Maybe that maybe that 5 minutes diatribe should have been on streaming, but it was not. So for those that didn't show up, make sure that you tell them the benefit, especially of the state issue, because employers need to be getting that message. Why isn't our talent staying in the state? I can tell you exactly why. Our exit interviews have consistently shown much lower salaries in this state than even just going across the border, by the way. And there are several borders around us, even going to Colorado, even going to Iowa, or even Missouri. There's substantially higher pay rates, 30% higher according to our exit interviews. All right? So keep that in mind. Let's see. I want to make sure that I'm actually, let's see. I don't have, okay, I don't know if the audio is working, but if you want to check it out on YouTube Live, let me know that if it's not working, that is. So again, this is kind of an end cap to the first start, or the first half of this this course. And I'm glad that she came here today, because it kind of ties into a lot of the things that I'm going to be talking about today. But it has more. I'm going to start out with talking about multi-tier architecture, which is basically what you've been doing in this course up until this point, and you'll continue to do it. But also it was exemplified in your most recent lab 9, and again, lab 10 next week. Everything that you've been doing up to this point has basically been a small self-contained program. You might have been doing some text or file data processing. It's all run locally on one machine, whether or not you were running it on the server downstairs or locally on your own machine. Usually it's single user, single threaded even. You might have done some thick GUI programming, like Swing or GTK, like we used GTK last semester to make a calculator and stuff like that. But it's little to no interaction with other programs. But that's not how software works. The vast majority of software is actually built to interact with not humans, but with other software. Most software exists not to solve a problem, but to interface with other software. We call this glue code, because if you've got system A and system B that need to talk to each other, you need to write the glue code in between that translates data, translates rules, translates whatever you want back and forth between the systems. And that's what we call glue code. And the vast majority of software is actually glue code. You're just interfacing with another system, right? Large, well-designed applications make then use of architectural design, because at the point that you no longer have a self-contained program, you've got many different programs. In fact, you can go take this to an extreme. It's called microservices, if you've heard that term. You can break up your application into a million little pieces and have those little tiny pieces all talking to each other, right? That's one extreme, right? Again, the best kind of design is somewhere in between, right? That you break up your application into parts until breaking it up any further no longer gains you anything. But you want basically what's called loose coupling because of the large scale here. Software design is on a larger scale. You need to think architecturally, not just how do you design a room, but how do you design an entire building? And how do you make the rooms work with each other? How do you design an entire city if you're a city planner, right? So you need to be thinking about design on a much larger scale. It makes use of these larger software projects, make use of extensive use of databases, as you've already seen, or data sources, and multiple data sources. You could be going out to Google Maps to pull GIS data. And then you could be going out to social media to pull Twitter feeds or something like that. And then you could be going to another database, a user database, and pulling in data like that. In fact, the way that we assign graders in this course, it's a Python script that brings together 3 different systems. We have to bring in Canvas, we have to bring in a user database for CSE, and then I have to finally interact with CodePost. So I had to write not an enormous amount, but a substantial amount of glue code to bring those 3 completely different systems together to be able to talk to each other to actually assign graders to all of your materials. So even that small little thing, it's a small task, right? I just want to assign graders to you guys. That makes use of 3 or 4 different systems, all of completely different technology. It has to be distributed. It should be multi-user. And you need to organize responsibility and interaction into what are called tiers, right? And that's what we're talking about today, multi-tier architecture. I would say beware. Now this is still true today. Architectural design can be loaded with buzzwordiness, all right? You will get seminar salesmen trying to sell you on some new product or some new framework every other week, right? The JavaScript, JavaScript front-end ecosystem exemplifies this. How many JavaScript frameworks does everybody have you heard of? Angular, and Angular 2, and they're completely incompatible, by the way. And what else? React. Right? What? Vue, V-U-E. Right? Got about a third of them that I could name off the top of my head. There are at least a dozen of them. And they all basically do the same thing. They all do model MVC architecture. Why do we have so many of them? Again, because everybody needs to create a new product and they need to sell that product, right? There are lots of weasel words like enterprisiness, right? I think I've shown this to you before, but there's a repo out there for FizzBuzz, enterprise FizzBuzz, and you can see how complicated it can get with over-engineering, right? Remember the Yagni principle throughout your entire lives. Yagni was what? You ain't gonna need it, right? You don't need to over-engineer your solutions. Look for the right solution, use the right tool for the right problem. Right? It's plagued with fads. Now this was, I still call this a fad, but cloud computing. Cloud computing is nothing more than doing stuff over a network. And guess how old that is? At least 60 years, right? We just wanted to come up with, we needed to come up with a new name so that we could sell stuff, Amazon Web Services or whatever Microsoft's product of that is called, right? Et cetera, et cetera. In fact, she was talking about MLB. She mentioned the Diamondbacks. The only thing cheaper than a Diamondbacks ticket is a Brewers ticket. So, any Brewers? I thought there was one Brewers fan in here. Anybody? Okay. All right. Well, you got Yelich, so you have reason to celebrate there. Right? Anyway, she was talking about MLB. Do you know what MLB's #1 revenue is? Server space. MLB TV, they got into the game really, really early on streaming live games, meaning that they were able to build up an infrastructure to serve live stuff. I think HBO actually pays MLB, or the structure that was built by MLB to actually serve HBO online. A bunch of other companies now pay MLB or whatever. I think that they had a spin-off so that they could change the business. But they built that infrastructure. It had nothing to do with baseball. It had to do with a product. It had to do with building an infrastructure in order to deliver live streaming stuff. And it was built so well that now it's become a product in and of itself. So cloud computing, what does that mean? Well, it just means that you're putting stuff over the wire. Who cares? Right? Oops, that's the last one. Right. In contrast to what you've been doing so far, you could call everything that you've done maybe in CS1 a single tier, meaning that there's only one tier. You put everything in, all the business logic, all the data manipulation, everything into one program, if it's C or if it's Java or something like that. For example, installed applications. If you install MS SQL, or showing my age there, Winamp, or Spotify, not the web application of Spotify, but the actual thick client application that you download and install. Those are all single-tier applications. You can treat them as single-tier applications. They're single user. If you save a file, persist data basically, you're saving it as a file on your own machine. It's not going out to the cloud and saving it externally. Might have terminals with networked file shares. We still have a few of those lying around downstairs. But it kind of looks like that. Now you can complicate that a little bit more with two tiers. So you've got a lot of interests here, right? Like with object-oriented programming, you might have the God class that does everything, sees everything, and you don't want to do that. That's an anti-pattern. You want to split that out so that one class is doing one thing, single responsibility principle. This idea can be applied to a more general situation where you've got architecture. I don't want this one system doing everything. It's managing data, and it's also processing and making a report. Let's go ahead and separate those out into a data tier and then what's called a business tier, or which also may include your interface. The client runs the application and has the business logic, maybe applying taxes or something like that. and the presentation. In other words, displaying the report or allowing a user to interact with the system. But a server on the back end, usually this is called the back end, handles the persistence of data. So like a true database. Instead of persisting to a bunch of CSV files, you're now persisting and saving to a relational database management system over the wire somewhere. It's more secure. You can provide more authentication, role-based data protection, etc. It's distributed. It supports concurrency. It supports multi-users now because you don't have everything tied up into one application that can only be used by one person at one time. Instead, now you can have multiple front ends by multiple users all accessing the same data tier in the back end. Well, there's nothing to stop you from going further, right? If you have a more complex situation, a more complex architecture, you can split it out into 3 tiers, and this is usually what's done. The database tier handles the data, right? So that's the same as in 2 tier. The middle tier handles the business logic and communicates between the client and the data tier. The client tier is the interface with the user in the system, and it's responsible for the presentation. In other words, actually acting with the user. Now, that doesn't have to be a human user. It could be an API, an application programmer interface, where another program is interfacing with that presentation and processing data back and forth. It sees the data in JSON or XML format, and it also sends commands back through that presentation layer. Again, it's not necessarily for humans. You might even be able to split this out into more tiers. In fact, that harkens back to something that that she said at the beginning. Right? Let's see. So it looks something like this. Again, you've got a database server down here, application server or business logic tier in the middle, and then client computers that are maybe accessing it through a web browser or a thick client application or something like that. Right? Oops. There we go. The whole point of this is that the separation of tiers allows for modularity at a large scale. Each tier can be completely different technologies. And so you can have completely different teams working on different tiers, and they don't have to interact too much as long as they've got a clear demarcation of responsibility between each other. But here's the data model. If you want to interact with it, you use our API over here. Okay, great. Now, as long as you don't change the API, right? Remember, this is dependency inversion. Rather than the middle tier depending on the data model underneath, it depends on an interface in between. And now they don't have to step on each other's toes. As long as the interface stays the same, we can program towards that interface in the data tier. We can program towards that interface in the business tier or the middle tier, and we don't have to interact at all, right? As long as nobody breaks that API. You can go for so for example. This loose coupling allows completely different technologies. Your database tier could be SQL Server or Postgres or Oracle or MySQL. And then as long as you've got that layer of API between them, that loose coupling, you could take that database, like say MS SQL or SQL Server, throw it out because you no longer want to pay Microsoft, and bring in Postgres, and the other tiers are completely unaffected because they weren't completely dependent on that lower level tier. There was a loose coupling. They weren't programming towards a specific database. They weren't programming towards a specific data model. The middle tier could be .NET, C# or JSP pages like you had in your lab yesterday, or Java or PHP for maybe, or C++, Perl, whatever, right? The middle tier could be completely different technologies, and you could swap those technologies out if you really wanted to, as long as you're conformant to whatever loose coupling rules you've established. There could be entire frameworks like Rails or you mentioned Angular, Vue. These front-end JavaScript frameworks that you can use can kind of achieve this. You could have thick clients or thin clients. You could have a thick client that's written in Swing or GTK or something that interacts with your business tier remotely, or thin clients, usually that means a web browser. That usually means a web browser, but of course now we've got things that we've always had in-betweeners. These are all dead, by the way. Microsoft Silverlight, Flash lived the longest. You can still find Flash games, by the way. But nobody does anything new in Flash, at least that I know of, and Java applets never really got off the ground. But a new in-betweener that you might not be aware of is, oh, dang it, now I forget what it was called. Atom.io uses it. It's basically a framework that packages up a web browser so that if you write something in JavaScript, HTML, CSS, You can package it up with this web browser. It ends up being like hundreds of megabytes. And you send it out, and it looks like a thick client application that somebody can just run up and install and run. But it's basically running a web browser, and that's what Atom.io is. Electron, that's it. Anybody ever heard of Electron? Okay, that's what Atom.io is. They wrote everything as a web browser basically, and then they put in Electron, packaged it up, and now it's a thick client application that you can install and run locally without a web browser because it's already a web browser. Also, RESTful services. So RESTful is representational state transfer. A lot of newer systems will be API first development, meaning that they will design the API with the intention that multiple different clients could come in and interact with their system. Then they'll write their own client and that interacts with that system. CodePost does that. CodePost has an API published, and that's why I adopted it for this course and others, because I can use the API to upload everybody's submissions, automatically write a script to automatically assign graders and everything. All I have to do is hit a button every week that we have something assigned. I made that investment by putting in 10, 20 hours, whatever it was, of programming so that I didn't have to solve that problem ever again. But I was only able to do that because they designed it with RESTful services in mind, that I can interact with their system any way that I want through their API. Now, I don't have to build a web application like they did. Of course, they built a web application on top of their RESTful services that interacts with their RESTful services, and you can go there and you can log in and you can look at all the stuff through a web browser. I chose to interact with it programmatically through their API. And a lot of applications are written with an API first design in mind, that you design these web APIs first, and then you build the back end and you build whatever front end you want. You can imagine the reason that you would want to do this, right? Do you want to, if you're Netflix can be delivered on dozens or hundreds of different devices, right? iOS has a Netflix app. Android, you can do it on a computer, you can do it on a TV, you can do it on a VCR, you can do it on a DVD player, right? So 50 different devices. Do you need to rewrite every single line of code for each one of those? No. You have a core set of pieces of functionality that you put on a server, and then you only rewrite the front end for each one of those things that you want to support, for each one of those systems that you want to support. And RESTful services, or distributed services like that, facilitate that kind of design. More complex systems might require greater abstraction and interaction. You could have 7 tiers, a 7-layer burrito if you want. In fact, I've got an example here. You could have a database layer, which is just a regular old database. On top of that, and I should have inverted this, but on top of that, you could have a data access layer, so that you're not actually writing JDBC code, like JPA. You could have a data access layer written in JPA or ADO, that's Access Data Objects, Abstract Data Objects, I think, with C#. I forget what it was, but you can have another tier on top of that so you don't have to write SQL code directly. Instead, you use that abstraction on top of it. Then you could have a first level business tier, a core level, that has functionality that's basically invariant across all different clients. This harkens back to something that she mentioned. Fast enterprises build software for government services. A lot of those government services are the same. So you can take all those the ones that are the same and put them into one layer, and then on top of that, you could have a second customized tier where, okay, this state does taxes slightly different. Okay, we'll build a module for that on top of this stuff that then talks and translates between those two layers, so that you don't have to reinvent this entire layer down here. You can take common functionality and put it into one layer, and then have customizations on top of that. You could have a data validation layer, right, where data is going from some front-end applications down through the layers. You could validate that before it comes in. If it's tax services, you have to verify that this person is actually living or something like that. You validate the data. You validate. It could be even as simple as validating an email. Is it syntactically correct? And 2, if we ping it and send an email to it, does it actually come back with a response? Because we don't want just a bunch of bots accessing the system or something. So we could have a validation layer between those two things. We could have a presentation layer on top of that, and then what we like to call a template layer on top of that. Because if you're selling the same banking software, or like Fast Enterprises is selling the same productivity software, or whatever it is that they sell to government services. Of course, you don't want Michigan having Nebraska's, what is it, the SOAR? What is the SOAR? It's just the SOAR on top of the Capitol. You don't want Michigan to have the SOAR on the templating layer on their website, right? So you can have a layer on top of that that provides templates, that provides branding to whatever client you sold the software to. In fact, we had that embarrassment a couple of years ago, didn't we? It was the wrong SOAR that was put on license plates, I think. So, right? It wasn't our SOAR. It was Minnesota, or no, Missouri SOAR or something like that. I don't know. But the wrong branding, which if it were on a website, that'd be embarrassing. But if you had a templating layer, you could easily fix that without having to touch any of the other database layers, right? So again, it's easy to generalize this into whatever tiers you want. You can completely distribute it, and that's where microservices comes in. And you have a million different tiers, and all those tiers interact in 50 different ways instead of having this hierarchy. It's a big giant web of interconnectedness. And that's just another way to go, not necessarily the best way to go, but that is a possibility. Scalability may demand that you actually do this and that you distribute it across different hardware. For example, if your website is getting hit by now millions of users, you can't have just one server serving those millions of users. You're going to have to have another server in between that then distributes that load onto different servers. You try going to Amazon sometime and looking at the IP address that you're actually resolving to, then go back to it the next day. It'll probably be a different IP address because Amazon would have redirected you to a different server to handle your shopping needs, right? You can also have, all of this stuff can be packaged up and sold, right? Just like I said, that MLB, one of their biggest revenue generators is selling server space and server needs. Amazon, I don't know if their revenue has gone beyond that. Certainly their margins are the best with their Amazon Web Services probably. They're just selling software as a service, or the last one, their IaaS, infrastructure as a service. They're selling you their entire they have millions and millions of data, or of computers in different data centers across the world. They're selling you time on those servers, and that has become a big data revenue for them, because they built that infrastructure because they wanted to sell stuff, and then they realized, hey, we can commoditize, make this entire software, this infrastructure that we've built, we can make that into a commodity and sell that as well. And that's becoming really popular. SaaS, that's software as a service, platform as a service, networking as a service, or infrastructure as a service. That's kind of an umbrella that captures them all. And you can sell all this stuff, right? And lots of companies do that. And you can decide, do we want our own database server? Is it worth the investment to buy a $10,000 database server, or is it cheaper just to pay Amazon Web Services to store our data? We'll go ahead and have an application server over here, but we'll let Amazon Web Services handle our data tier, right? Or maybe you purchase one from Amazon Web Services, purchase server space from Microsoft, and then you glue them all together, right? I don't know that many people do that, but you could do something like that. And then you can pay for software as a service. You can pay Google for GIS data, geographical information services systems data, right? Google Maps, basically. So lots of complex things here, and immediately raises questions. What should I do? How many abstraction layers should I have? Who should I be paying for all this stuff? Do I go to GoDaddy for my SSL certificates, or do I try to self-sign and not have to pay anybody, right? What tier should be responsible for what? Do I need a thick client or a thin client? Should we make a web app version of this, or should I just go with an Android application or an iOS application or something like that? How do we manage our data? What languages do we use? What platforms do we use? What technology do we use? All of these are huge questions if you're facing a startup or just want to get started in something. Those questions are easily answered if you look at it from a business perspective, because most of those questions are going to be answered by external factors, external constraints, right? For example, user base. There's no reason to invest $1 million in hardware if you only have 10 users to start out, right? You try to look for a platform or an infrastructure that can scale with your needs. You make a small investment up front, and then if you get more and more and more users, then you start buying more and more hardware or start paying Amazon Web Services to scale up. At some point, maybe Amazon Web Services becomes so expensive that you say, nope, we're going to make that investment and we're going to build our own data center or something, right? The size, location, requirements, this is why they build data centers in the Midwest. Do you know why they build data centers in the Midwest? Cheap land, cheap electricity, and goes back all the way to something I said at the very top. Unfortunately, cheap people, right? They can get away with paying lower salaries in the Midwest than they can. Imagine opening up a data center in the middle of San Francisco, right? You're paying 10 times that much for the land. You're paying 5 times as much for the electricity, and you're probably paying 3 times as much for the personnel. Right? And that's why so many data centers are built in the Midwest. Also, way more amenable governments to giving them nice tax write-offs. Right? So, thankfully, citizens are starting to wake up to that in certain places and saying no to that kind of stuff. That's why. Who didn't build the data center in Washington because of that? Was it Amazon? I forget. Their headquarters, Amazon headquarters, ended up not building in Seattle or wherever it was because people fought back against the tax breaks that they were trying to give them. And of course, another external factor is your budget. How much money do you have? Can you raise capital? Right? This is known as the iron triangle of projects. It's not just software projects, by the way. This is any project that you can consider. Correctness, quickness, cheapness. You can choose 2 of those. You can't choose all 3. Meaning that if you choose to do it correct, sound, well-designed stuff, and quick, it ain't going to be cheap. Right? You're going to have to pay for the personnel. You're going to have to pay for the infrastructure services if you don't want to build them because you want to do it quick, et cetera, et cetera. If you want to do it quick and cheap, it's probably not going to be very good. Right? If you want to do it correct, sound design, everything like that, and cheap, it's probably not going to be quick. It's probably going to mean that you're not paying as many people as you need to be. You don't bring up as many people on the project, and so it's going to take a longer time. And this is known as the iron triangle of software development or just project development in general. Anything, building a building, right? You can choose 2 of those, but you can't choose all 3. Right? Although you try to as much as possible. That's why we see the rise of I forget what the architecture is called, but like the newer dorms they're not dorms, but the newer apartments. That 3-tier kind of architecture. You see that all over the place now, especially where the top 2 tiers are apartments or residential, and then the bottom tier is some sort of a business or office kind of space, and that's because it's really, really cheap. Look at the building materials on that stuff. It is all pure wood. A 3-story major building, all built out of wood. So be careful next time a tornado comes around, right? That's not standing up. If you're in the nice, big, giant concrete dorms, you'll be fine. Right? All right. So all these questions come into play with software as well. Can we do it cheap? Can we do it quick? Right? You could, of course, choose fewer than these. You can choose none of these. You can choose to do it, or just one of them. You can choose to do it quick and really expensive and not correct at all. Right? You could choose to do none of them. We'll do it incorrect. We'll do it. It'll take forever, and of course, it'll be really expensive. And that's where boondoggles come in. Have you ever heard of the term boondoggle? It's basically where a company is able to either grease the palms directly or indirectly of the right government officials, so that they can get the contracts and they can end up not doing the right amount of work. When the website, one famous instance of this is when the website went up for the ACA. That's the American Healthcare Act, the Healthcare Act, right? The Obamacare website went up. That was notorious. It was terrible. It was really expensive, way over budget, and it was not delivered on time at all. And it was not necessarily a boondoggle, but it certainly had the smell of a boondoggle. And I can tell you many more boondoggles that have happened over the last few years. You can recognize them pretty damn apparently. Systems evolve, and so whatever answers you came up with over here could drastically change even 6 months from now. Again, maybe you had an excellent product and everybody is just chomping at the bit to get on your website or whatever, and now you've got 1 million users overnight, right? Now you might need a significant additional changes. Additional layers might need to be introduced so that you can handle that kind of load. It might require refactoring of functionality, right? Maybe you did it quick and it wasn't necessarily correct, like you've done in your many people have done with their projects. They didn't do it right the first time, so they had to find time to do it over, and that's called refactoring. You go back and you fix it to make it more maintainable, so that you aren't fighting your own code. There are also there are also migrations. Say that again, a SQL Server no longer serving our needs. We need a distributed system. We'll go ahead and change over to Postgres. That means that there's going to be a migration. That means that there has to be a migration plan. There's got to be a development, and basically you're going to be supporting 2 systems in parallel for a while. You'll have some sort of a changeover, and then you will still have persistent maintenance after that in case there are still problems. So basically with the migration, you are committing to double the work for a certain amount of time. And so all those cost factors have to be brought in, and you have to really think about that. Is the migration worth it? Right? Or is this legacy system that's green screen, can we live with it a few more years, right? Well, it's not broken. If it ain't broken, don't fix it, right? And many people choose to do that. And that's why only 3 years ago did we stop offering Fortran as a programming language, because there are still legacy systems out there, NASA mostly, that still rely on some variant of Fortran, and it's still being widely used to this day, right? Has anybody ever heard of now, dang it, I forget what it is. Has anybody heard of Adobe, what is their language? Not Firelight, what was it? Dang it, Cold Fusion, that's it. I was thinking Fire, it was just the opposite, Cold Fusion. So has anybody ever heard of Cold Fusion? One, two, all right? It is a language that shot up overnight and almost just as quickly died. But so many systems were written using it. It's kind of like an in-betweener it's kind of like Flash. It was Adobe's version of Flash. As so many systems, so many people developed Flash applications, you can still find job listings for Cold Fusion applications. You can still find job listings for Cold Fusion applications for maintenance and kind of stuff, right? In fact, a year or two ago, somebody asked me, I've got 2 internship offers. One of them is working on Angular 2 and web app development, and the other one is something, and they told me it's something called Cold Fusion. I've never heard of that, and so which one would you advise I take? I said, take the Angular one. All you're going to be doing for the summer is maintaining a bunch of legacy code that nobody cares about, but is mission critical and needs to be maintained in some way. That will not, it won't help you on your resume going forward, because certainly 5, 10, 15 years from now, nobody's going to be using that garbage, right? So you should even if you're not going to use stuff, even if you don't know about Rust, say, or you don't know, you're never going to learn Rust, or you're never going to learn Cold Fusion, you should learn about these things because it provides a valuable lesson about fads that come in overnight, and about legacy systems, and about making the correct decisions. Sometimes it's a gamble, right? The people that decided to make a bunch of Cold Fusion applications, they were gambling in some sense on this new shiny thing over here. Oh, Adobe, that's a big company. They're going to support this forever, right? Well, they were making a gamble, be conservative, right? This is why a lot of systems certain languages don't evolve that much, like C. C only makes small changes every 10 years. Why? Because they don't like to gamble like that. They don't like to gamble that things are going to change so drastically that everything falls apart, right? There's always a nice little dance here of finding the Goldilocks zone of learning something new and shiny versus being conservative and stuck 30 years ago, still doing your own memory management. There's got to be some, compromise in between there. All right. Good design, again, is true abstraction, loose coupling, making sure that your modules, or it could be individual classes, or all the way up to entire subsystems or tiers, have loose coupling, that you could take out one tier and throw it away and replace it with a completely different technology and nothing breaks. That's good loose coupling because it makes it so that it is flexible and you can change your designs later on. Good modularity means also using interoperable standards and protocols. These are kind of old now. WSDL is Web Services Description Language. Of course, XML and now JSON I would add to that list. ECMA, anybody know what that is? JavaScript. ECMA script is just the official standard for JavaScript. Even that's, so a couple years ago I said maybe JavaScript will be dead in 5-10 years. I don't think that's true anymore. But because of something else coming along called, has anybody ever heard of WebAssembly or WASM, WASM WebAssembly? It is an attempt, and it's kind of been stalled. That's why it hasn't made any progress. It's been an attempt to try to get rid of JavaScript by making transpilers. So you can write an application and say Java, transpile it to WASM, WebAssembly, and have it run on any web browser because it transpiled into a subset of JavaScript. And it's been the dream of WASM to get rid of JavaScript and replace it with anything that you want as long as it compiles to WebAssembly. Again, software as a service-oriented architecture, having multiple access methods, an open web API or something like that will mean that you have true loose coupling, and then you can have an Android development team that uses your API, an iOS development team that uses your API, and a web development team that uses your API, and you don't have to repeat this for every single platform that you want to deliver it on. Right? Bad design is just the opposite. The demarcation of responsibility becomes blurred. Your data tier goes into your business tier, or your presentation tier is in your business tier, your middle tier. Storing business logic in the database, like running full procedures or running full business logic, like computing taxes or something in the database itself. That's using stored procedures. That's probably not very good design. The presentation logic might not be separated. I've seen this plenty of times where people have written Java code that generates HTML code. Rather than just putting HTML code directly into a JSP page. All of these tiers then become intertwined, and you've got spaghetti code at the architecture level, right? Where there's no demarcation of responsibility. Bugs are harder to track down. And now everybody has to be, you've probably heard it before, a full stack developer, right? That's a smell. That's kind of a smell if you ever see an ad for it. We're hiring rockstar full stack developers, meaning that they want you to do every single job. They want you to be a database administrator. They want you to be a developer. They want you to be a front end developer. They want you to be a debugger. They want you to be a QA. Because they don't want to pay 5 different people to do 5 different jobs. They want to pay one person to do 5 jobs. You should not have that in a sufficiently complex. Now, if it's a simple system, sure. If it's just a basic CRUD application where you're just putting stuff into a database and serving it, fine. Be a full stack developer. But if you've got a sufficiently complex system, then no way is that going to happen. You need DBAs to be DBAs. You need front-end developers to be front-end developers, and you don't want them to step on each other's toes. You also have something called technical debt. Remember, if you don't find the time to do it right the first time, you're going to have to find time to do it over later, and you're basically taking out a loan on your time. And I've got a footnote here. If you're interested, it's actually not a technical debt. The real term, the real analogy to trading would be a naked call option. So anybody in here Wall Street bettors? Wall Street bettors. Do you know what a naked call option is? All right. So I'm selling the option to buy a stock. Say I'll say for $50, I will buy Google stock from you at $100 7 days from now. Something like that, right? It's a naked call option because I don't know, nobody knows how much Google stock will be worth 7 days from now. In other words, I have no bound on my loss. right? Google stock could be worth 0 if everything keeps going as it is 7 days from now. And I could say, I'll buy all your stock for $0, and I win big because when the market comes back, now it's going to be worth a lot of money. Or maybe Google announces that they've had a breakthrough in quantum computing, and overnight now the Google stock is worth $10,000. I have to kind of come up with that $10,000 to buy the Google stock, to buy your Google stock. It's a naked call option because I do not know how much I'm putting at risk. And that's exactly what technical debt is. You don't know how much time you're taking out of your future because you're doing something wrong. It could be, oh, well, it never comes up. The bug never manifests itself. Okay, then I got lucky and Google stock went to 0 and I was able to buy it all, right? Or I could get really unlucky and it completely crashes the system. We're down for a month or we go out of business, right? And now that kind of technical debt was a huge, major naked call option, and I was not able to cover it. So, Wall Street bettors, just one of them. All right, it's a very nice subreddit to laugh at people, but do not get involved yourself. Right? Just be a lurker. Right? Don't bet yourself. So successful design actually requires the perfect storm of good design, appropriate resources, competent developers, motivated developers, sustainability, and good management. There have been plenty of studies on this 4th bullet point here. There have been plenty of studies that show that people start introducing bugs because they get bored with the software. If you get bored with the software, if you get bored with the problem that you're solving, you kind of lose interest and you start to make mistakes because you're not as diligent as you were. Right? So you need to have motivation, and this is why maybe changing jobs every 2, 3, 4, 5 years, whatever your comfort level is absolutely essential to just keep yourself sane, because there is no such thing as lifetime employment anymore. Do not think that. Certainly it hasn't existed for the last 20 years. We're talking about a boomer generation that thinks that you should stay at the same company. In fact, even pre-boomer generation that thinks you should stay at the same company for the rest of your life. Do not get complacent in that thinking. Again, one of the limited ways that you will ever make huge gains in salary increases is by continually changing jobs. I had a colleague once that he had been at the same job for like 10 years, but every summer he sent out applications to everywhere. And he went out on interviews every summer. And he told his boss every single summer, I'm going on a job interview. And his boss would say, okay, good luck. And by the way, when you come out back, let's have a performance review because I am going to give you a raise so that I can keep you here. He was very, very open about it. Now, in some company cultures, you do not want to be open about it. You do not want to say, yeah, I'm job searching, because then at that very second, they start looking for your replacement. It is okay to change jobs. Just have a job offer in hand before you go to your employer and say, what can you do for me? And even if you have a job offer, it's 30% higher, and you go to your current employer and say, what can you do for me? And, oh, well, we can match that. Okay, well, then I'm going to have to go through this process next year too to get the same raise. I'm going to have to go through this process the year after that, right? And they'll never pay higher, right? They will only match offers, right? And maybe, unfortunately, in a lot of company cultures, even though they'll match your offer, that's just so that you don't leave in 2 weeks. All right, they might then start the wheel grinding to find a replacement, and you should be aware of that. You should be comfortable with that and knowing that, because that will inform your decision on they were paying me 30% less for the last 2 years. Do I really want to stay here? Right? And if I stay here, how much of the clock do I have left before they replace me with some intern? Right? So you need to learn about company cultures. You need to suss that out. You need to use resources like, say, Glassdoor. And you need to feed back into those resources. If you have an excellent internship over the summer or the next 2 summers or whatever, make sure that you put that on in Glassdoor as feedback so that company has built up a reputation and other people will know that this is a good company to work for. Or if you have a bad experience, make sure that that's on there too. 3-tier architecture is usually presented as MVC architecture, which is a popular realization of 3-tier architecture. It's actually quite old. If you see any blog posts, again, seminar salesmen, fads and stuff like that. Everybody thinks that they will have reinvented three-tier architecture. Or, oh wow, I found something new. It's called MVC Architecture. We really need to start using it. Well, it's what, 50 years old now? It goes back to Smalltalk. It's a design principle and is often and can be broken. It kind of looks like this. The model, of course, is going to be your data tier usually. The controller is your middle tier, your business logic. And the view is simply just the presentation layer. And each one of these may talk directly to each other. Like if you're just pulling data to display, the view can go directly to the database, pull that, and then display a table of all the data. Or it can interact with the controller because somebody inserts a new album record like you'll do next week, right? On your own, remember the post about COVID-19, right? No lab next week, everybody got points for it, but you still need to do it because it's essential for your assignments. But you have basically a model view controller in your last two, in Lab 9 and Lab 10. Again, this is the presentation layer, this is the middle tier, this is kind of the data tier. I'm going to go past all this stuff because this is what you actually experience. This is one realization. This is the JSP model. This is one realization of model view controller. You had a web browser that went to either a servlet, which was the middle tier, or it went to a JSP page to display stuff, or an HTML page or whatever. And then between that, you had a model, and usually that's called in Java they call them Java beans. And that basically had a connection to your database. In the database, there was an album table. The Java Bean, there was an album class, right? And there was a one-to-one correspondence between those things. And so you had a web browser that made requests to the middle tier, and it went that might have gone to a Java Bean that went to a database to pull that information, to pull it back into the JSP page that served it out to the web browser. Every time you asked for refresh that album list or whatever. You were building, I believe, this part right here that actually went to this part right here where it actually went to the database. You were writing JDBC code in some sort of a Java and creating instances of an album or instances of a band to serve back to the front end over here. Some other additional frameworks that are Java related, et cetera, et cetera. This is an even bigger picture of a three-tier architecture where you have the database and then a middle tier going back and forth, but you can also have parallel or orthogonal systems. Say that you want to go to an external data source like, I don't know, if you're doing money management systems, then you could get the current stock price of Google stock right now. Right? And then you're not actually writing that software, you're just using that as a software as a service. You're going out to like, I don't know, Yahoo Finance. I think that they have a free API. And you can pull Google's current price here, and then maybe persist that bound to the database, or just use it in your application layer. You can go out to Google Maps, GIS data, and pull that into your application. So you're not just contained to your own three-tier architecture. At every level here, actually, you can have some sort of orthogonal dependency on an external system like this. Right? So in summary, again, this is kind of an end cap to the first half of this course. All this stuff falls under the banner of software engineering. And we do have a software engineering program, just like we have a computer science program and a computer engineering program. At the end of the day, don't worry about it. Everybody interviews for the same jobs. There's virtually no difference on the jobs that you'll interview for. But the only difference would be computer engineers. You might have a little bit easier time going to like a hardware development company like Garmin or something. Garmin does a lot of embedded systems programming and stuff like that, and they look typically for computer engineers instead. But otherwise, everybody is going to be interviewing for the same jobs. Under the banner of software engineering, you have software development methodologies. Waterfall is an old school one that I would not recommend. What we've kind of been following is Agile, right? So this project has been, split up into what are called sprints: 2-week sprints, 3-week sprints. We took the project and we broke it down into those sprints, and we told you that those are the sprints. What do you do at the beginning of every sprint? You plan ahead. These are the things that I'm going to do for this sprint. These are the things that we told you you're going to do for these sprints. But we did give you an opportunity to design it up front. Right? You design it up front by drafting your design document and taking full advantage of that feedback. Then you actually implement it, and at the end of each sprint, you look back and you do a retrospective. Right? Assignment 4 retrospective, assignment 3 retrospective. What went well, what didn't go so well. Right? And if you're doing this in an actual software development team, you're doing it as a team. At the beginning of the sprint, you would commit. You decide. It's the agile software development is self-managed. The idea is that you got rid of managers, the Dilbert kind of like managers, the pointy-haired managers, and engineers should be managing engineers. That's Garmin's philosophy. And so at the beginning of each sprint, the engineers get together as a team and say, for the next 4 weeks, these are the things that we'll commit to. Right? And then they even have these things called burn down charts, where, okay, each day you update your project and this is the amount of work that we committed to at the start. This is 0. We should be making linear progress towards the end of the sprint. And if you're not, or if you're seeing huge jumps back and forth or something like that, then there's something wrong with how the team is developing. The whole purpose of doing this kind of planning, this kind of sprint planning, is to even things out, so that you don't have these large spikes in activity and these low troughs where you're not doing anything. Try to even those out so that you're always working at a constant level, so that you can work ahead, and then and if something does come up, then you can go ahead and say, all right, well, we're not going to be able to commit to that anymore, but we've planned ahead, so we know what we're going to be doing. There's also business requirements, design specifications, use cases. Right? These are all kind of things that we've either given to you or that we're trying to have you suss out with your design document. There's also testing and quality assurance. Unit testing, which is covered typically in Computer Science 1. Integration testing. Once you've got 2 modules or 2 systems, you want to see that they're actually talking with each other. Automated testing, regression testing. Regression testing is where you go back and you fix a design flaw that we pointed out to you, but you're not changing the functionality. So if you've got 100% on your correctness, but you missed 25 points on your design, go back and fix that design to address those points, but that should not change your correctness, right? You still need to get the same answer out of that. If you break it and it does cause an issue with your correctness, that's called a regression. And that's why you need good testing, because you don't know whether or not you broke anything. Regression testing is, we made a change, it wasn't a functional change, but did we break anything in the process? Performance and load testing, right? You might be able to test your server. It worked when I went to it, but then when 1,000 people are going to it, it suddenly breaks, right? You used to call that slash dotting. Now it's probably called, or the Reddit brigade. All right, we'll go to, hey guys, here's an interesting website. It's on some crappy web server. 1 million people try to hit it at once, and the crappy web server goes down. We used to call that slash dotting. Does anybody know slashdot.com? That used to be the de facto tech kind of website. And anytime Slashdot reported a link and it made it to the front page or whatever, then you had 1 million people hitting it, and it went down immediately, and it was called slashdotting. Right? It didn't hold up to the load testing, and so you do need to do load testing. If my sorting algorithm works when I try it with 1,000 elements, when I try it with 1 million elements, it takes 10 years. Right? That kind of testing needs to be done. Right? Also, version control. I would say ignore. Only use get one. One thing I don't have up here is Mercurial. Anybody heard of Mercurial? It's another distributed CVS. No? All right. That's because it never got off the ground. Bitbucket used to be Mercurial, and then they adopted Git because nobody was using Mercurial. But everybody uses Git now. If you do not know Git, or if you're not using Git for this course, get on the Git bandwagon. Right? You will be using it for the rest of your foreseeable future until something else comes along to replace it. CVS ruled for 10 years. Then SVN came along and ruled for 15 years. Git, I don't know how much of a life cycle it has right now, but it's at least 15 years old, maybe 20 years old, and it's not going anywhere. It won. It won the battle. Right? How much longer it's going to continue to be the winner, I don't know, but you definitely need to use it and have that in your toolbox. Build and deployment measures. You can be a DevOps engineer. Right? Does anybody know what DevOps is? Development operations, where your application is so complicated that building all the code and deploying it to multiple different servers becomes a job in and of itself. When I worked at Werner Enterprises, we had 2 DevOps people. This is before they called it DevOps. But we had two people whose entire job was doing nothing more than making build scripts. They never wrote any single line of software. They just wrote software to build and deploy other software. It was two full-time jobs. And you can get into it now, and it's called DevOps. Make, Ant, Apache Maven, all these things are build tools in C or in the Java world. Right? NPM, anybody know NPM? Node Package Manager, stuff like that. Right? All that goes into kind of DevOps. Right? And when something breaks, then you need somebody that knows what they're doing, specialized, very, very specialized kind of things. Right? Also, you need to be a bit of a lawyer. Like she was talking, the Fast Enterprises works with a lot of government agencies. Government agencies have a lot of regulations that they need to adhere to. For example, Sarbanes-Oxley. That was an act put into law right after the Enron scandal. That said basically if you're a large enough organization, you need to have every single action ever performed on paper or recorded, right? And you have to be auditable. Every single dime that we spend to bring in candidates and go to lunches, we have to make sure that every single dime is accounted for. When I go to a lunch with a candidate, I cannot get a simple receipt and pay for it. I have to get an itemized receipt because it will go into the system and it is completely auditable. Right? An auditor would come in and look at every single thing, every single penny that we've ever spent for any effort, and we have to justify it. NIST, National Institute of Standards and Technology, or HIPAA for medical stuff. If you're working for a medical company, you guys fall under FERPA. I have no idea what that stands for, but it's basically if your parents called me and say, he's not getting a good enough grade, I say, I can't talk to you. They're protected under FERPA. Your parents cannot know what you're doing or any of your grades or anything like that. In fact, I've had people contact me. I said, well, FERPA, go talk to a lawyer, right? And it's great. I love it. I don't have to talk to people. Right? So, in sum, if you're going to be a software engineer, software developer, whatever you want to call yourself at the end of the day, you got to be a little bit of a lawyer. You got to be a little bit of a philosopher, a diplomat, definitely, because that's the soft skills, working with other people, right? You have to be a designer, certainly. A manager, because most software teams are self-managed nowadays with agile software development. You have to be a writer, right? We already covered that with technical writing. And last, and maybe even least, you have to be a programmer. Right? I think that there are a lot of software developers out there that will say that 90 or 80% of my time is done doing this stuff up here. The thing that I love the most is actually programming, but I only do it like 10 or 15% of my time, right? Because I'm doing all this other stuff. Because if I just programmed day in and day out, I'm not working with other people. I'm not thinking about my design. I'm not thinking about the implications of what I'm doing or software that I might be stealing and opening up my company to not simply just stealing software, stealing a line of code to plagiarize for a homework, but now we've stolen an entire code base. And now we can be sued, and our company is going to go under because of it, right? Et cetera, right? You have to be all of these things, and maybe last, and maybe certainly least, is going to be a programmer. Right? So, as you are matriculating for the next 3.5 years, how many years you've got left, be thinking about this. You have to be all these things, and that's why a liberal arts education is still of paramount importance. Questions? No? All right. That was more opinion than anything else. So take it with a grain of salt if you want. But